We're going to go over organic chemistry questions, and the first one we have here: a compound with a general formula of CnH2n can either be an alkene or a cycloalkane. Some of these compounds exhibit cis and trans isomerism. Write down 3D structures of the isomers, include the stereochemistry, and give you pack names for 2-butane. Now, when you're talking about 2-butane, butane meaning 4 carbons, and there is a double bond at position number 2 there. Want to write the 3D structure, so I'm going to show the atoms the way they are arranged. So we have got a carbon double bonded to another carbon, and then we can have another carbon here where we've got now CH3, and then another carbon here where we've got also CH3, and then an hydrogen attached at this end, and then an hydrogen attached at this end. So these two are on one side, and then I can also write another one CH3 there, but the other one, the CH3, I'm going to put it down, or I'm writing like this because I want a carbon to be direct bonded to another carbon. And then there's an hydrogen there, there's also an hydrogen here. So we can see here the methyls are on two opposite sides. So this would be, so the way I've written it, really it won't show the stereochemistry here. Stereochemistry, we want to understand whether it is going in the board or out of the board. So instead, the way I've put these bonds, let me remove these bonds. Okay, so the attachment of the methyls, I'm going to remove them there, and I'm going to show whether they are coming in the board or they are coming towards us. They are entering in the board or coming towards us. That would be the stereoisomerism. So if this one is entering the board, we are going to show it. If this one is coming towards us, then we'll show it shaded. But let me say this one is entering the board, so we're going to use these lines, meaning it is going in the board. Even this one is going in the board. And then the hydrogens are pointed towards us, so we are going to write like that. And also this hydrogen here pointed towards us. And here for also this one, the hydrogen here is going in the board. Here the methyl is also going in the board, but the methyl here is coming towards us, so we'll write that one shaded. And also this one is coming towards us, so also shade it. Now we can give the UPAC names of these. Well, we can see that here the methyls are both going in the board. So because they are all going in the board, or they are on the same side, this is going to be called cis. Okay, this is going to be cis-2-butane. And then here, this methyl is going in the board, this methyl is coming towards us. So this is in opposite directions. That is going to be called trans. That would be trans-2-butane. So that is going to be it for this question. And another one we've been given here: natural gas, a widely used energy resource, is a combustible mixture of hydrocarbons, including largely methane and a small proportion of propane. Give a balanced equation for complete combustion of propane in excess oxygen. Or propane, we know alkanes have got the general formula CnH2n plus 2. Then propane has got 3 carbons. That is going to be C3. H, we put 3 there to be 6 plus 2, that will give us 8. So this is a gas, and it gets to burn in oxygen. Also gas. This is going to give us combustion, complete combustion, as we've been told. Complete combustion here produces carbon dioxide and water. Incomplete combustion produces carbon monoxide and water. So we're going to have carbon dioxide as a product, and also water as a product. Now we need to balance this equation. So to be able to balance the carbons, I'm going to put a 3 here because I've got 3 carbons. And then I'll balance the hydrogens. We've got 8 hydrogens on that side. I'm going to put here a 4 to balance it. Now we can see 3 times 2, that will give us 6 oxygens, and then 4 oxygen this side, so giving us a total of 10 oxygens. So to make them 10, I'm going to put a 5 there. So that is a balanced equation for the complete combustion of propane. And then part B, we have been told several constitutional isomers can be written for the molecular formula C5H10O. Calculate the IHD for C5H10O and state all possible interpretations, including possible functional groups. So IHD, which is the importance of hydrogen deficiency, is given by 2N plus 2 minus hydrogen divided by 2. So this is going to give us 2. N is the number of carbons. We've got 5 carbons plus 2 minus hydrogens. We've got the 10 of them, and then divided by 2. So 2 times 5, this is a 10. It will cancel with this negative 10, and we'll remain with 2 over 2, which is a 1. So 1 IHD means we have got either one double bond, or we have got one ring without a double bond. So the possible functional groups, let's first look at those functional groups which have got an oxygen and yet they also have a double bond. What functional groups are those? We have got a double bond, a carbon double bonded with an oxygen. This can either be a ketone or an aldehyde. So these are the first two functional groups, ketone and aldehyde. But we said it can also be a ring. So the only way it can be a ring is when there's no double bond. And because we've got oxygen, it can be a cycloalcohol, where it is an alcohol in a ring form. So these are the possible functional groups that we can have for this IHD. And then part 2 of question B is saying, draw a cyclic secondary alcohol with the molecular formula C5H10O. Now a cyclic alcohol which is secondary, when you're talking about alcohols, a alcohol has got OH functional group. So if we have got an alcohol having a carbon, and then this carbon there's a group R attached to it, this is a primary alcohol because there's only one group. But we've got this carbon directly attached to the OH. If it is bonded to two different groups, that is going to be called a secondary alcohol. When you have got now this carbon being bonded to OH, and then it has got three different groups. Well, this group should not be an hydrogen, it's just the three different groups. Then this is going to be a tertiary alcohol. So that is how we tell. Now, so this is a secondary alcohol. That means it should be a carbon bonded to the OH, and it should be bonded to two different groups. So it should have a group this side and a group this side. But remember, it should be a cyclic secondary alcohol. So already we have got one carbon here and we have got another carbon here. No, I'll not show that carbon because we know that when we just show a line like this, it means there's a carbon at the end. So we have used up already one carbon, two carbons. We are remaining with how many carbons? We are remaining with 3 carbons, and those 3 carbons should form a ring. So that should be a ring of 3 carbons. So I'll show it like that. So this is a secondary cyclic alcohol. We can count if the atoms are balanced. At each end there is a carbon here, and the carbon is only having one bond this side. That means you should have 3 hydrogens, because a carbon, for it to be stable, it needs to have 4 bonds. And then this carbon here, you can see there are only 3 bonds, 1 there, 2 there, 3 bonds. That means it should have an hydrogen. So there's another bond with an hydrogen there. This carbon here, it has got only 3 bonds, 1 there, 2 there, 3 there. So it means it should have 1 hydrogen. And then this one should have 2 hydrogen because there are only 2 bonds, and then 2 hydrogens because there are only 2 bonds. Let's count the hydrogens are present. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10, this one which is here. So this has proved for the molecular formula that we have there. So that is it then. Now, part 3, draw a ketone with one methyl group as a substituent with the molecular formula C5H10O. A ketone with one methyl group. Well, this formula has got 5 carbons. So if we remove 1 carbon to form a methyl, we're going to remain with 4 carbons in the main chain. So this will be position number 1, number 2, number 3, and number 4. And for a methyl, it should have a double bond with the oxygen. So already this carbon which is here has got 4 bonds, 1 here, 2 here, 3 there, 4 there. So it doesn't need anything else to react with it. So the methyl group, we are going to attach it to this carbon. Okay, that is where the methyl is going to be attached. We can't attach it at this end because it will no longer be a methyl group. The longest chain will be 1 2 3 4 5. It will no longer have a methyl group because it will be considered as a part of the longest chain. So a methyl group is attached at that end. So this is going to be it. And this functional group, we shouldn't put it at this end or at this end. Otherwise, if we do, then we have formed an aldehyde. Okay, let's look at this one. Provide the IUPAC name for each of the following molecules shown. The first thing is we need to identify the function groups present. Well, for this one, we only have a double bond, so we need to always give priority to the double bond. We need to give it a lower number. And we can't start counting from here because if we start counting from there, then the only direction that we can go in this direction. We always need to make sure that the double bond is covered as we get to count the longest chain. And so in counting, we'll start from here: carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7, carbon 8, carbon 9, carbon 10. What if instead of us going from position 7, instead of us going forward, if we went down 8, 9? So we see we would get few number of carbons. That's why we would rather go straight. But if there was something again like this, so this would have given us 8, 9, and then 10. We wouldn't have gone straight, we would have gone in this direction. Why? Because we would rather go in the direction that will give us a lot of groups other than going in the direction that gives us only one group, because this will just be considered as one group. But since this one has given us a lot of carbons, we don't have a choice but to go in that direction. And the groups which we have got at position number 7, we have got an isopropyl, methyl, methyl, and methyl. We first need to name that one which comes first in the alphabet. Iso. I comes first than M. So at position number 7, we have got isopropyl. So 7 isopropyl. And then at position number 3, we have got a methyl. At position number 4, we have got a methyl. Position number 6, we've got a methyl. 3 of them, so we'll put trimethyl. This chain has got 10 carbons. That will be called decane. So I'll say dec. At which position do we have a double bond? Position number 2. Dec 2N. So that will be the name. Or if I want to not write like that, I'll just say trimethyl and then put the position of the double bond at position number 2 and then put decane. Oh, so that is another way that you could have written it. So that is it for that one. Now let's consider now part B. How do we get to name it? Let's identify the function groups present. We have got an alcohol. This is a methyl, so always need to give priority to the alcohol. So we'll start naming from here. And then we're going to go in the direction that will give a lower number to the other group that we have. So we'll go in this direction: 2, 3, 4, 5, and 6. So we'll first name the group. At position number 3, we've got, how many carbons does this have? 1, 2. It has got 2 carbons, so that is an ethyl. So this will be 3 ethyl. And then the parent chain is a cycloalkane. So that will be cyclohexane, but it's not an alkane, there's an OH, so it will be cyclohexano. We have not even put the position of the alcohol because at any point where the alcohol is located, that is what will be considered as the first position. Let's consider this one. Name the functional groups in the following structures. So what are the functional groups present in the first one? So this functional group here, a carbon double bonded with an oxygen, is a carbonyl group, but specifically because it's on the middle of the chain, it's a ketone. If it was at the end of the chain, it would be an aldehyde. And then we have got also a carbonyl here, but it is directly linked to an OH. So when a carbonyl group is directly linked to an OH, it's no longer a ketone or aldehyde, but it will be considered as one that is a carboxylic functional group or carboxyl functional group. Okay, carboxylic acid functional group or carboxyl functional group. And then let's look at this one here. We have got the OH. This is the alcohol functional group, which is the hydroxyl functional group. And then we have got N is amine. Now when N is direct linked to a carbonyl group, it's no longer amine. When an amine is direct linked to to a carbonyl, it's no longer an amine but amide. We consider it as one. So that is an amide functional group. Well, we also have this one. This one is an aromatic functional group for a benzene. So we have got alternating double bonds. That's an aromatic functional group. Now the following names are incorrect. Give the correct two-pack name for each of the compounds which are given here. So to be able to give the correct two-pack name, first we need to draw the way they've given us. So this one is 4-ethyl 5,5 dimethyl pentane. This is showing is a pentane, meaning it has got 5 carbons. So let's draw that. 1, 2, 3, 4, 5. And this is telling that at position number 4 we have got a what? At position number 4 we have got an ethyl. So let's name 1, 2, 3, 4, 5 there. So at position number 4 I've got an ethyl. And how do we show an ethyl? An ethyl is like this. Okay. Two carbons. And then at position number 5 we have got, at position number 5 again we have got 2 methyls. We can see 5,5 dimethyl. Position number 5 we have got 2 methyls. Position number 5 is here 1 and then 2. So this is the structure for the name which has been given, but what will be the correct name? So to tell which one is going to be the correct name, let's identify the longest chain. We are going to start at N1 end of this chain. We can either start from here, 1. So if we start from there, then position number 1 is going to be here, number 2, number 3, number 4, number 5, number 6. That will give us a long chain. Or we can as well start at this carbon 1, 2, 3, 4, 5, 6. So we see that whether we start from here or we start from here, we are all finding position 6 as the longest chain. But we need to go in the direction that will give us a lot of substituents as groups. So if we start from here, we are going to go straight like this. We are only going to have one group as an isopropyl. But when we start from here, we are going to go in this direction. We are going to have a methyl here and an ethyl as groups. So we need to go in the direction that gives us a lot of groups. So therefore, we are going to name in the direction that gives us what? A lot of groups. So the correct naming will start from here. 1, 2, 3, 4, 5, 6. I'll not start naming from this direction because the groups are going to receive very big numbers. So ethyl comes first in the alphabet, so this will be 3-ethyl. And then at position number 2 we can see there's a methyl there, 2-methyl. And then the whole chain has got 6 carbons, that is hexane. So that will be the correct two-pack name for this one. Let's also consider B. We've been told 4-methyl 3-hexene. So hexene meaning there are 6 carbons, 1, 2, 3, 4, 5, 6. But this is a 3-hexene. That means at position number 3 there's a double bond. So 1, let me get to name it. 1 or number it 2, 3, 4, 5, 6. Position number 3 there is a double bond. So at this position. Now at position number 4 there is a methyl. So at this end there is a methyl here. Okay, like that. So what would be the correct name for this one? Well, we need to make sure that the double bond receives a lower number. So if we start in this from this direction, it is receiving position number 3. Let's try to start in the other direction. 1, 2, 3, 4, 5, 6. Starting in the other direction, it is still receiving position number 3. We will not give it 4, we will always give it a lower number. But as we get to name, we always need to make sure that also our group receives a lower number. So if we start in the direction that you started in this direction, we are seeing that the methyl is going to receive position 4. But if we start in this direction, the methyl is going to receive position number what? 3. So we name where it will receive a lower number. So this is going to be 3-methyl. And then At position number 3, we have also a double bond, and then hexane. So that would be 3-methyl 3-hexane. So that would be the correct name. Let's consider this one. Describe the type of bonds present in the following molecule. So we have got H, C, triple bond to another C, and then there's C, double bond to an oxygen, there is O, there is H. So what are the types of bonds in this molecule? Sigma bonds or pi bonds. Now, whenever we look at this, we see it's only a single bond. This is always a sigma bond. And then here, there is one sigma. So here there's only one sigma bond, but where there's a triple bond, there's one sigma bond, and there are two pi bonds. And then here, we only have one sigma bond. Here, we also have only one sigma bond. Here, we only have one sigma bond. And then here, we have got one sigma bond and also one pi bond because it's a double bond. So the pi bonds here are formed due to parallel overlapping of p orbitals in this case. So when you have got, let's talk of just here where there is a triple bond. So if we look at this carbon here, it's only bonded to two things, this side and this side. So the kind of hybridization for this carbon is sp because it's only bonded to two things. And then if we look at this carbon also, it's only bonded to two things. So also the kind of hybridization is sp. Remember there are three p orbitals. So that means p of the orbitals are not hybridized. So what we are going to see is we have got this carbon, we have got also this carbon. So we have got two hybrid orbitals, sp hybrid orbitals. One is going to come in this direction, and then one will go in that direction. And then the other hybrid orbitals from the other carbon will be like that. They are going to overlap. So each of these orbitals brings with it one electron from one carbon like that. So this head-on overlapping is what forms a sigma bond, which we can see. And then this side, this is where we can see another carbon, which will bring also its orbital. So that is it. So this is an sp orbital. But this carbon here is bonded to three things. That means it has undergone what? sp2 hybridization. So this orbital you can see is sp2 hybridized. And then this side there is an hydrogen which has also brought its electron, and the hydrogen only has an s orbital, and then this is an sp orbital from the carbon. Also this one is an sp orbital from the carbon, and then this also is an sp orbital from the other carbon. Now there are two orbitals which are not hybridized. I'm interested in showing those. There are two p orbitals which are not hybridized. So let me show that. This carbon has got a p orbital which is not hybridized. Even this other carbon here has got a p orbital that is not hybridized. So these two we can see they are going to form parallel overlapping like that, and that is what forms a pi bond. And it's not only one, because it is only sp hybridization. There are two p orbitals which are not hybridized. So there is another one which is not hybridized, and that one we are going to see there is one there, another one there, and also for this other carbon, one there, another one there. Well, these are not passing over each other. The one I've put in blue and the one I've put in green, they are not passing over each other. We can think of it like one is like this and then another one is up like that. So it's just a drawing which can show that exactly. And these two are also going to overlap like that. Also that side are going to overlap. So this is what is going to form another pi bond, forming two pi bonds, and two pi bonds, those gives us a triple bond. So that is it for this one. Calculate the IHD for C6H10NO2Br and state all the possible interpretations. So IHD is equal to 2N plus 2 minus H divided by 2. And this is going to be equal to 2, the number of carbons, there are 6, plus 2 minus the number of hydrogens in this case. How many hydrogens do we have? We have got 10. Now we also have an halogen bromine. For halogens, we always subtract them so that we only have one hydrogen. And then we have got a group 5 element. For group 5 elements, we always add their IHD. It's only one. Oxygen is in group 6, and those don't affect IHD, divided by 2. So this is going to give us negative 1 plus 1, that will be a 0. So we only have a 10 there. 2 times 6, that is a 12, plus 2, 14. 14 minus 10, that is a 4. 4 divided by 2 is a 2. So what does this mean? When we have got an IHD of 2, this means we either have 2 double bonds. Okay, we have got 2 double bonds, or we have got 2 rings without any double bonds, or we have got 1 ring and 1 double bond, or we have got only 1 triple bond. So this is the meaning. When you have got an IHD of 2, it means 1 triple bond or 2 double bonds. Okay, like that. Or even 2 rings. Now let's answer the next question. There are a number of compounds with the molecular formula C6H10NO2Br. Draw a 5-membered ring structure that is a carboxylic acid. So this should be a ring, but it is a carboxylic acid, and it should be 5-membered. So 1, 2, 3, 4, 5 carbons there, and then we're going just to join those. So there are 5 carbons here, and remember in the formula there are 6 carbons. So the 6th carbon is what is going to come here and form a carboxylic acid functional group. So we can count if the atoms are balanced. In here, this carbon which is here has got 2 bonds, so it needs 2 more hydrogens. So I'll just put 2, meaning there are 2 hydrogens. Even this one needs 2 hydrogens. This one needs 2 hydrogens. This one needs 2 hydrogens. And then this carbon here has 3 bonds, so it only needs 1 hydrogen. So how many hydrogens are here? 2 plus 2, 4, 6, 8, 9, 10. This one, and we can see we have got 10 hydrogens. And then there are 6 oxygens. And then there are only 2 oxygens, this one and this one, and that balances this one. And then we are remaining with what? We are remaining with a nitrogen and also a bromine there. So where are we going to put those? A nitrogen and a bromine. So we want to draw this one, which is here, a 5-membered ring structure that is a carboxylic acid. So where is the nitrogen going to be? And where is going to be the bromine? Okay. So we can have bromine at any position there. And we can also have nitrogen at any position. But whenever we've got a nitrogen like this, a nitrogen can't exist alone like that. It should have 2 hydrogens with it. It can't be just nitrogen. It will not be stable. It needs to have at least 2 nitrogens. So a nitrogen should be in this form. It should have a R group here, a R group there, a R group there. It's a derivative of ammonia, these amines. So that's how it should be. Now, is it still balanced? Is this molecule still balanced with the atoms that we've been given? Let's count that, we see if it's already balanced. So we've counted for a nitrogen, so we can remove a nitrogen from here. We've counted for the bromine, so you can also remove the bromine from there. The 2 oxygens, we've already counted for them. The 6 carbons, we can see already we've already counted for them. Now let's count the hydrogen. There should be only 10. They should give us 10 hydrogens. So at this point, we have 3 bonds, so we only need 1 hydrogen. And then 2 hydrogens there. Well, at this point also we have got 3 bonds. We only need 1 hydrogen. At this point, we have 2 bonds. We need 2 hydrogens. We need 1 hydrogen here because there are 3 bonds. We need 2 hydrogens here. So let's count 2, 4, 5, 6, 7, 8, 9, 10 there. So this is the structure then for that molecular formula. Again, I'll repeat, never write nitrogen alone. It won't be balanced. nitrogen should always be attached to some hydrogens or so, or to three other groups. Now let's consider part 2. We want to write a six-membered ring that has a nitro group. Six-membered ring that has a nitro group. Okay, so let's get to write that. Six-membered ring. So one, so a six-membered ring like that. And by the way, as we even drew this, we also cater for the IHD. Remember we calculated IHD of 2. This is one IHD. This is also one. A ring is one IHD. A double bond is one IHD, giving us an IHD of 2. So that's why we said we can have one ring and one double bond. Now here we are. We have got a six-membered ring, and it should have a nitro group. What does nitro group mean? NO2. This is a nitro group. So it should be one of the groups. So let's show that. It can be anywhere at any position. But we should also have a bromine, because a bromine is part of this chain. Okay. Bromine like that. Now, does this one have an IHD of 2? Okay, does it have an IHD of 2? So to understand that, we need to understand the bonds which are formed in what? In this compound. Are there double bonds there? Yes, they are there. So it would be having an IHD of 2. Just to confirm that, we can calculate and get to determine whether the atoms are balanced according to this general formula that we are given, or the molecular formula. So we're supposed to have 6 carbons, 1 there, 2 there, 3 there, 4 there, 5 and 6. So 6 carbons. And we need to have only one nitrogen, which is already here. And then we need to have 2 oxygens, which are already here. We need to have a bromine, which is already there. Now what we just need to determine, are there 10 hydrogens? So let's get to determine that. So this carbon here has got only 3 bonds, so it needs one more hydrogen to be stable. This one needs 2 hydrogens. This carbon here has got 3 bonds, so it needs 1 hydrogen. This one needs 2 hydrogens. This one needs 2 hydrogens. And this one needs 2 hydrogens because it has only 2 bonds. So how many carbons are here? I mean, how many hydrogens are here? 2, 4, 6, 8, 9, 10. So it's already balanced. So this is the ring for that general formula if it is supposed to have a nitro group. Now let's consider this one. Draw the molecular orbitals of ethene. Ethene is a hydrocarbon with 2 carbons only, CH2, and then how many hydrogen? This is an alkene. An alkene has got the general formula CnH2n. So if it has got 2 carbons, then it's supposed to have 4 hydrogens. So we can also write this as C double bonded with C, and then there are hydrogens there. Now I want to draw the molecular orbitals. So the first thing we need to understand is the hybridization. So we can see this carbon has got how many, is bonded to how many things? 1, 2, 3. It has got 3 bonds. So it is undergoing sp2 hybridization. Even this one is also having 3 things around it, so also sp2 hybridization. Okay, now we can draw that. If it is sp2 hybridization, remember there are 3 p orbitals, then that means there is one orbital that is the unhybridized. So when you have got a carbon here and then another carbon here, 3 of these orbitals, sp2, means we have got 3 orbitals which are hybridized. So I'm going to show those which are hybridized in white. So we're going to have one this side, we are going to have another one there, we are going to have another one there. And then also from this carbon, we are going to have one which is going to overlap. We're also going to have another one. We're also going to have another one. So I'll just say white is going to mean these are hybrid orbitals which are sp2. And each of these have got an electron. One electron from each carbon. There's one electron there, one electron there, one electron there, and electron in the same orbital should have opposite spins. We need to also note that. Now from here we have got two hydrogens attached on each carbon, so there's going to be one hydrogen here, another hydrogen there, another hydrogen there, also another hydrogen there, and each of these brings one electron with them. So this one brings an electron, should have opposite spins, brings an electron, also brings an electron there. So in this case, the ones which I've written in yellow, those orbitals I've written in yellow coming from the hydrogen are s orbitals, and hydrogen has got only one electron. And then we have got one p orbital which is not hybridized. So I'm going to show it. Let me show it like that. Even on this other one, there's a p orbital which is not hybridized. So I'll show it like that. So these two get to overlap up and down. So the way we are going to see that is because of that overlapping, they are going to come like this. So they overlap on top and also down. And each p orbital from these contains one electron. So there's one electron from each orbital. So this p orbital from one contains one electron, and this p orbital contains one electron. And that overlapping is what forms a pi bond, which also caters for this double bond which is here. And then this head-on collision is what forms a sigma bond which is present there. So that is going to be it. Now we've got another question here. Draw the structures for, we have got trans 3 bromocyclopentane carbohydrate. So this is trans 3 bromocyclopentane. So I'll first draw the cyclopentane. Should have 5 carbons in forms of a ring. So they are like that. And then it should be a carbohydrate. Now, whenever we hear of a carbohydrate, this means it's an aldehyde where the functional group, the carbon in the functional group, is not part of the longest chain. Now, because of the word trans, I'm going to put stereoisomerism. Let me put like that at this position. This is where I'll put now the carbohydrate. So there's a carbon at this end, and then I'll put the O there, double bonded with the oxygen, and then an hydrogen. There's a carbon here. The functional group for an aldehyde is C double bonded with oxygen, and then there's an H here, there's an other group here, and in this case the other group is this thing which is here. I could have as well shown the carbon there, but it doesn't make any difference showing it. So at position number 3, because priority is to the what? To the aldehyde. At position number 3, in whichever direction that we start counting, we are going to have a bromine. So if I'm going in this direction, then this is position number 3. We are going to have a what? We are going to have a bromine. And because it is trans, it should be towards us. Since the functional group for the aldehyde is going in the page, then this should come towards us. We need to show the stereoisomerism there. And then this is bromine. So this is trans 3-bromocyclopentane carbohydrate. Okay, now for part 2, we want to write pentanamide. So pentane just means it has got how many carbons? 5 carbons. 1, 2, 3, 4, 5. Now this should be an amide. Amide, the function group for an amide is a carbonyl attached to an amine. So in this case, I'll not attach this group, the pentane, to this one. Otherwise, the name is going to change. So I'm going to put the double bond with an oxygen here. And then now I'll write the NH2 at the end. That's the functional group. So position number 1 of the carbon, number 2, number 3, number 4, number 5. This is pentanamide. Let's look at this one. Draw the structures whose UPAC names are given to pentanone. Pentanone meaning 5 carbons. 1, 2, 3, 4, 5. At position number 2, we have got whenever something ends in non, we should know that the functional group for that one is a ketone. So at position number 2, we've got a double bond with oxygen. So that is 2-pentanone. And then we've got 5-oxohexane nitrile. So first I'll draw the hexane. Position number 1, number 2, number 3, number 4, number 5, number 6. Now this, at position number 5, there is oxo. Oxo is a group name for either ketones or aldehydes when they're acting as substituents. So if this is position number 1, 2, 3, 4, 5, at this position, that's where we're going to have a ketone. And then this ends in nitrile. Well, the function group for nitrile is CN, a carbon triple bonded to a nitrogen. So this will be CN at the end. Now, if we put it at the end here, then this will no longer be 5-oxo. Then we'll start counting from this direction. This will be 2-oxo. So then the functional group should be at the beginning of the chain here. Okay, so that is it. So that when counting, this will give us position number 5. We'll start in the direction that will give a lower number to the group of highest priority. And then number 3, we have got butyl butanoate. Whenever butyl butanoate, what is this functional group which ends in OH? This is an ester, not ether. So ester. And an ester comes from a carboxylic acid when it is bonded, when it reacts with an alcohol. So this is how an ester looks like. When naming, we always start by naming this portion which is bonded to the oxygen. So this is where the butyl comes from, the part which is bonded to the oxygen. So butyl 4 carbons, 1, 2, 3, 4. And then I'll put an oxygen there. And then this oxygen is also bonded to a carbon that is bonded to an oxygen like that. And then now we'll write the other thing this side. It is also butanoate. So there are also 4 carbons. So the first one being this one itself. And then 2 there, 3, 4. So 1, 2, 3. The fourth one is itself here. So this is butyl butanoate. What of 4? We have got N-methylbenzamide. So I'll first write the benzamide. So benza means we've got a benzene. And the benzene is a 6-membered ring with alternating double bonds. So if we've got a double bond here, we're going to have it there, we'll also have it here. Because of resonance, most of the times we just see a circle inside there. So that is it now. This should be benzamide, meaning it's an amide. It has got a functional group for what? An amide. And how do we show that? An amide is a carbonyl bonded to NH2. Now, when you have got something attached to this ND side, if we have got one group attached to this side, then we're supposed to have only one hydrogen because this has got one lone pair. Remember we said NH2, but I've removed one H, I've put an R group. And when we are naming something that is attached to this N, we say N comma. So N, and then you name that thing which is attached there. So that is how it's going to be. So we're going to have a carbon that bonded to an oxygen there, and then we have got an NH, and then we have got a methyl attached here. So a methyl I can just show like that, a line, or I can write at the end CH3 like that. So this is N-methyl benzamide. You first name this group which is attached to the amine before you name the group which is attached to the carbonyl. So this, the whole of this functional group is amide. So why we see it ends in amide there. Now the last one on this one, methylbenzene. So simply put a benzene that's got alternating double bonds inside. Now it should have a methyl anywhere, so we can just put a methyl at any position. So this is methylbenzene. So let's look at this one. Compounds with representative formula CnH2n may be alkenes or cycloalkanes. Some of these compounds exhibit geometrical isomerism. Write down the geometric isomers and give you pack name of 2-butene. So geometric isomers, this is where now we find the trans and cis isomerism. So for 2-butene, we did it also earlier. We can have a double bond here. there's a carbon, there's a carbon. It can have CH3 that side, and then an hydrogen here, and then CH3 also this side, and then an hydrogen here. So I'm going to show the stereoisomerism on the bond. So I'll put lines like this, meaning it's going in the page. So I'm supposed to remove those straight lines I've drawn and put these, meaning it's going in the page. So let me just remove them so that it will not be confusing. Also this side I'll show like this, and then this one which is coming towards us, I'll use that, meaning it's coming towards the page or outside the page. And then I can also write another one where now the methyl group 1 is inside the page, whilst another one is going to be out. So I'll put an hydrogen here, and then I'm going to change the positions, and methyl is going to be here, which is CH3, and then we have got also an hydrogen here. So this one where the methyls are on the same side, this is called cis 2-butene, and then this is trans 2-butene. What of the next one we've been asked here? What would be the structure? Well, you can get to try it out even before you get to answer. So 1,3 dimethyl cyclobutane. So this is a cyclobutane. Butane with has got 4 carbons, but it is in form of a circle, so, or in form of a ring. So just get to draw that. At position number 1, if this is 1, then 3 will be here. If this is 1, then 3 will be here. So we can draw at any position. At position number 1, we have gone to have a methyl. So we can have a methyl here, CH3, and also a methyl here, CH3. I can as well write it like this, where I say this one is coming towards us or outside the page, and then one is entering in the page. So whether I show this one here and I draw it again here, it will be the same as this one. They are all going to be coming towards us. So one should be the same and one should be different. Where they are the same like this, then this is cis 1,3 dimethyl cyclobutane. And then for this one, just the same name which has been given, but we just get to put trans in front, and then we write the name. Draw structures of the compounds with the following descriptions. For part A, a straight chain primary alcohol with molecular formula C5H12O. This is straight chain primary alcohol. For it to be a primary alcohol, that means it is only bonded to a carbon that is bonded to only one group, and it should have this formula C5. So I'm going to draw a pentane with 5 carbons, an alkane with 5 carbons, 1, 2, 3, 4, 5. And then I just get to put OH at the end. This is the primary alcohol because this carbon has got only one group this side. Sorry, there's not even a carbon here. The carbon is at this position. So this thing has got only 4 carbons. 1, 2, 3, 4. So I need to put another carbon. So that carbon, let me add it this side. So this is now a pentane, a straight chain alcohol with 5 carbons. And then for B, a cyclic tertiary amine, molecular C5H11N. Now this should be cyclic and should be tertiary amine. And amine has got a functional group N bonded to a group there, a group there, a group there. And then it has got two lone pairs. So if this is supposed to be tertiary, a primary amine is bonded to only one ara group. A secondary amine, 2 ara groups. But a tertiary amine should have 3 ara groups. So we should have a ara group this side, and then an ara group this side, and then we should have also another ara group this side. But here it has got how many carbons? 5 carbons. Okay? So if this is 1 carbon at this end here, I can even get to show that CH3. Then how many carbons are remaining with from the 5? We're remaining with only 4. So again, we have got 1 here, 2 here. We are remaining with 2 more. So I'll draw it like this. So this is it. This is a tertiary amine with that molecular formula, and it is cyclic, where it has got a group at that position. Okay. And then for C, an allylic alcohol with 3 carbons only. What is the molecular formula of this compound? An allylic carbon, when we're talking of allyl, when you have got a carbon that bonded to a carbon, these carbons are called vinyl carbons. And then a carbon that is direct bonded to a carbon with a double bond, this is called an allyl carbon. So actually this group is what we call an allyl group when it is even bonded to something here. This is called an allyl group. So when we want an allyl alcohol, it is just C, C, and then there's an OH side. But this is bonded to OH, to hydrogen, because the carbon is supposed to be bonded to 4 things. Should have 4 bonds. This carbon has got only 3 bonds, so it only needs 1 hydrogen. This one has got 2 bonds, so it only needs 2 hydrogens. There and there. So this is the one. And I can just write it as here a bond, here a bond there, and then there. And then I can now put OH there. There's a double bond at this end. So I can also write it like this in skeletal way. Now what is the molecular formula? You can see we have got 3 carbons, and then how many hydrogens are here? 1, 2, 3, 4, 5, 6. So there are 6 hydrogens. But I'll not write the whole 6. I'll write 5, and then this hydrogen, I'll take it together with the oxygen as OH. So this will be the molecular formula. Let's consider now the last part in this practice. A frequently used food preservative P is made as shown below. So here we have benzoic acid. This is benzene with a carboxylic acid functional group there, and it's reacting with sodium hydroxide. Now this is an acid plus a base. What kind of reaction is that? For part 1, name the type of reaction. Acid plus base, this is a neutralization reaction. So what is the structure P? So P is the one which is used as food preservative when these react. So when benzene gets to react with this, one of the product, this OH we can see, gets to react with an hydrogen there, forming water, and that water is going to be the Q. And then this P, the sodium which remains, will attach there and react with the oxygen. So what we are going to see is so alternating double bonds inside. There's a carbon there, of course they've not shown, so I'll not also show it. There's a double bond there, and then O, so the sodium is going to attach here. So that is going to be the structure of P. Now give the IUPAC name. Now this, when this OH group gets to react with hydrogen, that will form water, and then what remains, we can see this is the form as this. There's another group here, there's another group here. So it's just that this other group is now sodium. So this is an ester. And to name this, you first name this group which is here. In this case, it's sodium. And ester ends in OH. So this is sodium. And then this is the coming from a benzene. Okay? This is going to be sodium benzoate. So I don't know if I've left an N there to name it as sodium benzanoate. So sodium, since it's coming from a benzene, benzanoate. So that is going to be the name then for that compound. So, and that gets to mark the end of this video. Thank you so much. Hope that was helpful. Enjoy your day.